All right, and let me share my screen for the moment. So welcome guys to participate in the monthly development cycle reading group. This week we're studying the new paper on phasic policy gradient. This is the second week of the monthly development cycle where we usually focus on implementations. For the first week, we usually just read the literature. But for the following 3 weeks or even 4 weeks, we'll be focusing primarily on implementation and details. So I'll give a sort of a status update on what I currently have. Actually, yeah, before I jump in though, have you guys try to do the implementation and how was it run? Is there anything you find tricky, that kind of thing?
On my side, the trickiest thing is that if you could maybe bring the algorithm, there are like
yeah, I definitely can.
For the update iteration, there is like a loop over phases,
Yes.
then a loop over epi, ev, and then finally an eox. So I find it quite tricky to play around those. And beside that, I did some experiment with just if you could go up just a little bit regarding the policy network structure. Yes, this part. Like
Okay.
fit a pi and fit a v. I used your PPO artery.py, right? And I tried to implement that kind of structure, like an independent value function.
Yes.
And I tried different ablation, like for example, using the standard one. So far so good. But as soon as I introduce the independent value network to do the loss value and all that things, it does not work anymore. So that's currently where I am stuck actually.
Okay, sounds good. We'll we'll talk about that. So I'll be giving sort of a short status update, like what kind of things I've tried with and what are some of the results that I have. I think, the implementation in this architecture wasn't that bad for me, and I try to make it work for the first time with Atari. It kind of works. The agent is able to learn, getting about 300 rewards, but it's supposed to be better. First of all, I got it kind of working with PPO, so just modified a couple things to make it work. Let me probably try to highlight some of the necessary changes that needs to be made. So first of all, you just have to import the proction environment, and then you can just kind of set the gem ID to be this, proction start pilot or something similar. And also in the paper, they're using the normalized environment. So they're using this running means STD class that were usually used for the Majorco environments to keep track, to do reward normalization such that the discounted return has univariance 1. So those are the couple things they did. Other than that, everything else just kind of stays the same. But you have to modify the convolutional layers a little bit because the input is slightly different. So I think in the paper, they didn't use frame stack like in Atari, and they also didn't use LSTM. So instead of having frames equal to 4 over here, you just have channels equal to 3, and then fill in over here. And then basically you somehow design these layers, and then you pass in the observation to see, before the flatten, to see what they look like. Basically, after the 3 convolutional layers, it's going to look like 32 channels with 8 by 8 sort of height and width. And then you just flatten them, and then you have the neural network working for this particular domain. And I didn't run exactly 100 million like they did, but the agent is able to learn something, but it learns very, very slowly. So as you can see in the video, which may be a little hard to read, but it's able to kill off some of the drones, and then it just got hit and died. So that's kind of the performance that I have for now, but maybe next week I hope to run for 100 million and see how that turns out. Another thing is the implementation with PPG. So I think I might be able to give you a little insights on so how phase and iteration, how these things come together. So maybe let's delve into the source code a little bit. And this is kind of a discussion style. So if you have any comments, things you want to say, feel free to just interrupt me, and then we can discuss anything.
I was going to ask, since I'm new to this, where do you find all this?
Find all what?
The code, my bad.
So in our reading group, we're sort of developing a common library. So it's called CleanRL. The name sort of stands for Clean Implementation of Reinforcement Learning Algorithms, and we're basing our implementation on this PPO Atari Visual. So all of these code are dependency kind of free. So so it should be the case that you can just, copy these code into and create a file and pip install anything that you need, and it should just be able to run. So every implementation details pertaining to an algorithm stays within the single file. So it's, for research purposes, it might be a little slow, but every moving components of the algorithm.
Okay.
Yeah. Sorry for the confusion.
So one question. In your agent structure,
Mm-hmm.
is that's how the channels were 3, and I guess the lead batch size is 32. Is the kernel size 4? Is that what that 4 is?
Let me take a look real quick.
The studies kernel size.
That's the kernel size, okay.
Yeah.
I'm looking at the OpenAI version, and I guess they use different module for that. I guess they have Impala block and...
Yes.
Yes, this seems to be the standard, the DQN nature structure, right?
Yes, exactly. So for the in the OpenAI's initial experiments with Progen, they use the Impala big architecture, which we can probably check it out real quick. But to answer Ali's question, for the channel, I think 4 is the what's it called, the
kernel size.
Yeah, kernel size. Yeah.
I think. And the TPO implementation there earlier, was that 3? Did you change it, or I just have a different? I can't remember. When I closed your latest, I saw that change. I wasn't sure.
It probably changed. So the reason I at least changed one of them, because before the change, the last linear layer looks like this. So it's a 6x6 with 32 channels, reduced features. But I tried to play with the PPG's official implementation. What I found is that after the convolutional reduction, it still has 8x8 with 32 channels. So I just kind of tweak around these convolutional channels a little bit to match the reduced sort of channels and sizes. Yeah. So, hey Kevin, welcome. Hi. We're just sort of starting our implementation meeting on the Phasic policy gradient. Welcome to join us.
Great.
Yeah.
Thanks.
Sounds good. So I will continue on this. So basically for the PPG, to match the structure of the paper, this is essentially what I did. Does that look similar to your implementation, Rosalind? So you basically have a network, and then you have an actor and auxiliary critic. The auxiliary critic corresponds to this, and the actor corresponds to this. And then you have a critic that just has the same architecture, but should correspond to just this part of the PPG algorithm. Does that look similar?
Yes, that is the exact same thing. Yes.
Okay, and are you saying that...
Maybe I have one more layer for the critic and the actor blocks.
I'm not exactly sure if you should use the same exact architecture for it, but you probably... I think that's probably one of the things you should do, is to have the same architecture, but I could be wrong. So that's basically corresponding to the architecture. And as far as how you do the phases, initially I was confused. I was kind of confused as well. I wasn't sure what the phase is doing, but then it starts to make more sense to me. When you go to the PPG's official implementation and try to read it up, what you find is that they basically say ppl.learn for a fixed number of iterations, and then they say ppg.learn. So essentially, everything we have for the PPO will be sort of be encapsulated in this part, and then the PPG part is only the latter part. So in terms of the implementation, this is what it means. So you have the phase, which corresponds to this for loop, and then you have the policy update, which corresponds to everything we have in the And then you have this second for loop, which corresponds to everything we have in the PPO. So that also include notably the policy sample reuse, which is this e pi. And then in my implementation, I don't have like a EV, because since in the PPG paper they just say e pi and EV equal to 1, so I just kind of blend them together.
Yes. Makes sense.
Yeah, but that's everything is the same. The problem with this algorithm, in my opinion, maybe the biggest problem to use it is the empty buffer. So if you look at over here, they say initialize empty buffer B, and then they add a lot of things into B. So that corresponds to adding all of the observations and the value target, which is the returns, sort of the lambda returns into the buffer. But this blows up memory, basically. And then if
when they say add all ST VT targ, isn't this just a standard sampling process of the observation and all those things?
Could you say that again? Also, I think I might have a bug. No, it's fine. Okay, sorry. What do you say, Rasen?
They say in the second line of the algorithm is initialize empty buffer B.
Yes.
And just after that, there is perform rollouts under current policy. So I guess that's how they fill the buffer.
Yes. So no. So that kind of yes. So initially, I have an observation buffer for everything over here. So the rollouts collection is within these. So you collect for n time steps, and then basically you fill out the observation vector, and then at the end you clone it and append it to the auxiliary empty buffer over here.
So they use different data sources.
Yeah, so essentially, it would be the same as if we were to do PPO beforehand, but running the rollouts for 32 times and adding those 32 rollouts all together into this empty buffer, which is huge.
Indeed.
Right. So that's, for me, that's sort of the biggest problem memory-wise. So in practice, I think it takes... I kind of forgot, at least 5 or it was very notable. Something maybe 5 to 10 gigabytes of RAM. But that's not the largest problem for me. The largest problem is how you do the auxiliary updates.
Maybe before that, because you're storing the already PyTorch, the torch tensors, maybe that's why. But we don't really need them as tensors, right?
So it only costs GPU memory if you put it in the GPU device. So is that the problem you were talking about?
What kind of a memory explosion you were referring to?
It's this. So it's not that bad. It's not like a million replay buffer. It's not like a replay buffer with a million size that kind of blows up memory, but it's pretty memory intensive.
I see. No big deal.
Yeah. So in a way, so what happens is you take this PPO project visual, right? And if you run with the default parameters, what happens is that for the first 500,000 time steps, every observation is kept in this buffer.
Every observation, okay.
Yeah, that's what it turns out empirically. If you set this npi to be 32, which is their default parameter, for the first 500,000 time steps, you're storing every observation in this buffer, which is very huge. And so that sort of concludes this part. That part corresponds to this part of the source code. And then this part should correspond to this part of the source code. And basically you have all of the buffers, everything in B, and you need to take them out. But B is too large, so what they end up doing is to also use a mini batch for the B. And
mini
if
batches.
you... Huh?
Yes, mini batches.
Yes, so they use 16 mini batches. So what I found is that because you have 500,000 numbers of observation in the empty buffer, and even when you split this 500,000 buffer into 16 pieces, it's still too large for GPU. Whenever I try to put it into like 1/16 of the 500,000 observation, my GPU 6 gigs of memory blows up. So that's when that happens. And for next week, I could try to run it with CPU, which will circumvent the problem. But I think overall, the memory footprint of PPG is quite surprisingly large. So if you go to their official repository and check out the issues, there are already people complaining about it. So in fact, this person has 8 gigs of GPU and it still blows up. So I think that's kind of the main problem with the PPG algorithm, at least for the implementation now.
What did they run it on then?
I don't know. I don't think they posted in this paper.
But they were quite boasting something about being more efficient than PPU somehow.
I guess it can, but the costs of this algorithm might be just very high memory footprint, which maybe there's something that we can do to improve it, I guess.
I see. So it's basically improvement in sample efficiency of the agent at the cost of using more memory, physical memory, kind of trade-off.
Yeah. I also wonder if they could do something more like using this as a replay buffer, just kind of sample it and then do an update instead of cutting into 16 pieces or something, because at least it blows up my memory.
Free lunch.
Huh? No free lunch. Yeah, it's kind of the case. And another thing, which I thought was pretty interesting, is I did a little experiments with just using PPG on Atari and see if we can get similar results. Obviously, I didn't use similar hyperparameters and run for 100 million time steps. I just sort of tried to use the standard one, the ones that I think probably make sense. And it wasn't performing that well compared to the PPO. So notably, in 10 million time steps, it reaches around 305, but when compared with other algorithms, it's not that impressive. but maybe that's just some tuning that I can further do.
I would say 300 is not too bad.
It's not too bad. But with PPL, at least with OpenAI baseline simulation, it can achieve 400. So this would be kind of a comparison. And if you see the bottom line over here, that's PPG.
Is this your implementation on Atari? Is it using frame stacking?
Yes, it's using frame stack. So it has all of the same conditions as PPL Atari Visual, let's say.
Just the auxiliaries updates.
Yeah. So we set the policy updates to EPI EV to be 1, and then we have some sort of auxiliary updates. I forgot what was the exact parameters that I said, but we can take a look.
Got it.
Yeah, so I set 6 to be the auxiliary update, which may be too low. Which that might be the thing that's hurting the performance, but
still, it's the default value.
They don't have a default value for the Atari. That's just something that I said because of the memory requirements. So in other words, right, if you look at the pseudocode here, the lower you set this MPI to be, the more likely you're going to have enough. The lower the MPI, the smaller the buffer. So if you have a smaller buffer, it wouldn't necessarily blow up your memory. Or your GPU memory, I guess. Does anyone have any thoughts or comments on these?
Oh, by the way, I saw you have a new kind of computation for the KL loss.
Do I? Oh, I see. Yeah, so that's from the PPG implementation. If you go to their source code and you go to PPG, and then you search for this TD, this is how they calculate the auxiliary loss. Sorry, not the auxiliary, but the joint loss. They try to minimize this probability distribution shift.
I see.
Yeah.
I should have checked it earlier, but I kind of wanted to do a first run with no spoilers.
Yeah. I think that's also a very good way. I also have to say, even though they're using PyTorch, it's still a little difficult to read their code.
Probably since it's OpenAI, it has their baseline flavor of the modularity above everything else.
A little bit, but I think probably the biggest problem is they're still using MPI, and I think that complicated the code base a little bit.
No free lunch.
No. But yeah, so that's kind of where we stand. And a couple of things that I think are kind of interesting to talk about is another thing, is how they do the benchmark. So if you look at the ProcGen paper, so when they train the ProcGen, so this paper where the ProcGen initially came out, they use this repository to train to play ProcGen. And if you look at how they train, they use OpenAI Baseline's PPO implementation, which is which I claim to be exactly the same as our implementation, because I spent so much time on it and wrote up an article. But notably, is that I think in the Phasic policy gradient paper, they have a slightly different PPO implementation, and that can be somewhat observed in the performance as well. So this is their PPO performance, right? Reported in the PPG paper. Let's don't even worry about that. Just watch this. And on the right is the OpenAI baseline's PPO's performance, which should be over here. Do you guys in some so notice, right, this is running for
200 million.
yeah, 200 million, I think. And these PPG's experiments are ran with 100 million 100 million time steps. But I think in some environments, I see the PPO's OpenAI baselines implementation actually perform better. And that is a little concerning to me.
Wait, I remember the color on the plot in the left are actually inverted. Yes.
No. Well, so this blue color, blue color over here is PPG's implementation of PPO's performance, and the blue color over here is OpenAI baseline's implementation of PPO.
Okay.
Yeah. So the blues should be directly comparable. But just something that I thought was pretty different. Like, for example, Heist is an example. So after 1 million time steps, the PPG's PPO implementation reaches about 4. But in PPO's, in OpenAI baseline's PPO implementation, I think it reaches around 6. I try to count it, but since there are little charts, it's hard to keep track of. But I think overall, the OpenAI baseline's PPO implementation might perform better in some domains.
Not surprising.
Yeah, another thing is when I inspected the implementation from PPG's repository, something that I found is that there's some implementation details that are presented in OpenAI baselines, but not in PPG's implementation of PPO. For example, I think, so for example, this is how they calculate the value loss, right? Just 0.5 times blah, blah, blah. But in OpenAI baseline's implementations on PPO, they have a sort of co-level optimization called value function loss clipping, which is over here, where they do things a little differently. For example, so in a way, I feel like they're not making exactly the same comparison. Another thing is, if you look at the scale for the orthogonal initialization of the layer, they use sort of a scale equal to 0.1. But I think...
yes, they use 1 in the OpenAI.
Yeah, they have a different value, basically.
Yeah, they use 1.
No, well,
I noticed yesterday.
for the scale, right? In the end, yes. I don't think it's 1. I think so if you're in the middle of the policy, I think it might be 1. Oh, sorry, yeah. So the weights of the value output layer is initialized with scale 1, but the output of the policy layer is initialized with 0.01. So, so overall, I think there are just some, maybe some difference between PPG's PPO implementation and OpenAI baseline's PPO implementations.
Well, those are probably really minor differences.
Yeah, those are minor differences. What else? I think those are just the main ones. I don't see anything else that really jumped into me.
I see.
Yeah, but overall, I think PPG is still performs very well. If you compare, let's say, this orange line with the blue lines over here, orange lines usually is much better. So, big fish, let me see. Yeah. So anyway, those are just some, a lot of implementation heavy things that that may or may not have an impact on the performance. Any thoughts?
It's gonna be hardcore.
Yeah. I might try to run, with a CPU so that the memory wouldn't blow up. The GPU memory wouldn't blow up. But I think that in that case, then PPG will kind of lose a lot of the advantages of these auxiliary phase, because everything over here can happen on GPU. By the way, to sort of give like a demo, so this is when the auxiliary phase starts for PPGs using PPG's papers hyperparameters, and as I mentioned, it starts the first auxiliary phase at about 500,000 time steps, and then it just try to allocate a lot of memory, and it wouldn't work.
Well, actually, it says it only tried to allocate almost 2 more gigabytes, right? But there was already 3.8. And if my memory serves me correctly, the neural networks themselves don't take that much memory, probably 600 to 1 gigabyte max. So it might be just the operations of the earlier phase, policy, and the independent value update that are taking most of the space. So if you were to work around PyTorch's garbage collector and delete the operation, maybe you could have some more memory for auxiliary updates.
Probably. So a couple things to notice, I would say, is this. I need to open the right file.
But you said it's the buffer that is actually...
Yeah, it's a buffer. It's a buffer. So the algorithm terminates on this line. So first of all, I'm taking 1/16 of the buffer to this m auxiliary obs variable. Then the algorithm terminates over here. So first of all, this m auxiliary observation, the 16th of the total observation array already takes a huge chunk of the memory. And then when you get the value, it takes another huge chunk of the memory.
Okay, how about this? On your line 511 and 512.
Okay.
How about you? 8.
Yeah, those are on CPUs.
CPU already, okay.
Yeah.
Okay,
Yeah.
Never mind.
Yeah, I've tried many things to make the memory work, but... And also, sort of implementing PPG kind of makes me want to implement Impala. Just because the Impala's neural network seems to have made a difference. If you look at the Impala paper, this is sort of the two models that they propose. And this is kind of like the Atari nature kind of architecture, but this is the more advanced 1.6 million parameters architecture. And apparently, yeah, it's cheese, right? But the small architecture is still 1.2 million. It's still quite a lot.
More than the parameter count, it's the structure that is.
Yeah. In any case,
Oh, go ahead.
Yeah. I was just gonna say, in any case, Impala apparently has really good architecture as well. I tried to play with TorchBeast, and it has very high throughput. So it's especially good with the games like StarCraft 2. Because the environment takes a really long time to run.
I see they also use some LSTMs, even in the left one.
Yes. Yeah, so if you don't do the LSTM, I think maybe the parameters will be a little less.
So not only LSTM, but okay. Now they don't use any more frame stacking, it seems.
Oh, I don't know about Impala.
I see 3 channels directly, so I suppose it's a single frame.
No, those are the kernel size, not the.
Kernel? No.
Oh, you're talking about this?
Yes, the free and.
Oh, probably.
On the left one, you can kind of recognize the standard DQ and nature hidden feature sizes, right?
Yes.
And the kernel size are inside the boxes in any case.
I see. Yeah, they probably didn't use what's it called, the frame stacking, and it makes sense because they are using LSTM.
Yeah, LSTM, exactly.
Yeah, that makes sense.
So many details. Evil is in the details, as we all know.
Yeah. There's a lot of details to pay attention to. Yeah. But anyway, I don't have a lot more updates on this other than to say, I'll try to run it on CPU, see if we can reproduce the results from the paper. But yeah, do you guys have any thoughts? Especially, I guess, Kevin or Derek, is there something that maybe I was unclear about?
Not really. I only started reading this paper today because I saw your message and
I see.
wanted to check it out.
Nice.
Kevin, a bit more from here on.
Oh, Kevin, are you the one who submitted the PR?
No.
Okay, that was a different person. You're working on you're talking about the radar remote.
Oh yeah, I got a little thing running. I didn't message back yet, but I'll do that soon.
I see. Yeah, not a problem. Let me know, if there's anything I can help you with.
Yeah, I mean it's super simple. I pretty much just kind of spin up like similar to what the AWS example you had was, but I just connecting it with the array remote function. I
see. Yeah, very similar thing. Yeah, sounds great. But yeah, so this is kind of what the monthly development cycle looks like. We look at a paper and we tear it down, we really hope it has open source implementations so that we can look at its GitHub repos and try to get everything we can out of it.
Let's say that the tear down is reciprocal. Both ways.
Yeah.
Well, this is great. I'm excited to take part.
Yeah. Great to help you. Welcome. Really welcome. And also, by the way, if you guys are developing any kind of games, developing with different kind of games, we're having this project called OpenRL Benchmark, where we try to incorporate as many games as possible. So right now we have the Atari games, we have some StarCraft, we have some car racing, we have some Procgen. We're trying to get in as many games as possible, and there's one person who's working on this environment called Gridley. Also, he's trying to add it into OpenRL Benchmark as well. So if you're working on something and if you want to add it to over here to sort of as a library, please DM me and we can work on that. Other than that, I don't have any updates. Rosalind, do you have any other thoughts on PPG?
Not much. Great work as always. I think I have found quite some inspiration to debug my own.
Nice.
So thanks for that.
Yeah, of course. Thank you too. What about Ali? Have you had a chance to check it out? How are you feeling about PPG?
Yeah, I didn't get a chance to do the implementation over last week, but I am cheating by peeping into your implementation right now. And I was going to try it out on a few of the ProcGen environments. I see right now it's on StarPilot.
Mm-hmm.
I was wondering if by any of the other 15 environments that they list in the paper, or if that'd be worthwhile to test out.
Yeah, I think that sounds great. There's another 15 environments, and I think all you have to do is to change the gem ID, and it'll be quite interesting to know the performance in other environments and see if they perform well as well.
Yeah, because any variants.
Sorry.
Hi.
Also, do you happen to have some PPG or PPO results on coin run already?
I have not actually. I think the reason why they're using the normalized reward env is because their reward is kind of arbitrary. Like for the coin run, I think you get 10 reward for getting a coin, but that's just so random and probably a little too large. You should, I think maybe you should give 1 to make the update more stable. But since they're using the normalized env, it's probably the same.
I see.
Yep. All right. So for the next 2 to 3 weeks, we'll be sort of continue spending time on ProcGen or PPG or PPO on these topics, and looking forward to see what kind of things we can do with it. Can we reproduce the results? Maybe we use a CPU to at least run it and see eventually what we can come to an end. And I know this is kind of still up in the air, but does anyone have any idea for the next monthly development cycle? Any topics that they want to explore into, or any algorithm that they want to reproduce?
I saw we had already a PPO R&D.
PPO R&D? Okay.
Go over with the R&D module itself.
Yeah, that would be a good topic. You guys also don't have to answer now. This is also something to just think about, and if you have any interesting algorithms you want to implement, feel free to post it in the monthly dev channel, and then maybe that's something we can pursue
also,
for the next monthly. Yeah.
I think Dreamer is not the choice.
I heard about it. What is this? What is the name of the paper? Just Dreamer?
Tree to control.
Okay.
There is actually a fresh one which is called Mastering Atari with Discrete Word Models, which is the discrete version.
Mastering what?
Atari with Discrete Word Models.
I heard they have this thing called Dreamer V2, but I have no idea what that is. Is this what this is?
That's Dreamer V2.
Okay. Yeah, I heard a lot of good things about it. Maybe this is also something that we can take a look into as well. And since we have the Apex sort of architecture, it might be easier to do experiments. So for those of you who may not be familiar, DQN or value-based methods, they usually take quite a long time to train. Like for example, let's use Breakout as an example. When I run C51 and DQN on AWS, it costs 25 hours to run. In comparison, if you use PPO, it's really fast. It's only 5 hours. And if you're trying to read anything that is faster, there's the implementation called Apex DQN implementation that uses distributed experience replay. It's much faster, but the all of the open source implementation available, it's either very complex, like in a CDRL repo, by the entire library has like 20 or hundreds of files. It's very difficult to read. but we have sort of a single file implementation that performs pretty well. In 4 hours, it reaches 350. So, if we want to implement Dreamer, which I assume is value-based method.
Not sure.
Dreamer
model based,
value based.
Yeah, is this sort of
model based?
Yeah,
Well, there is model, but there's also a value, so you could say value based. Yes.
in other words, does it sort of do updates like DQN?
No.
Oh, it's
actually.
Huh.
There is one, right?
It has some sort of actor critic, so I'm not sure.
It still
Yes,
could be true.
The actor critic operates in the model, the virtual model, so that's why.
Okay, interesting. Yeah, I don't know.
It's actually a mix.
Oh yeah, okay. Maybe introducing the Apex DQN maybe not relevant to this paper. Yeah, but I think that might be something very interesting to look into as well. Do they have an open source implementation on this?
I do believe so. Maybe not the latest one, but Dreamer has open sourced the code.
Okay. Yeah, I only see the first one, I think.
Yeah, the Dreamer V2 is really fresh, so.
I see. Okay.
I
Reason.
know there's also a re-implementation in RLlib now. Just got added.
Oh, really?
Yeah.
Let's take a look.
You probably have to search Ray
Yeah.
RLlib. Yeah.
Good point. Oh, they updated the documentation site. Really pretty. RLlib, scalable reinforcement learning.
Under algorithms under that sidebar.
Oh, I see. I see. Dreamer, but it does not be Dreamer V2, maybe?
No.
Okay, I see. Yeah. So a lot of interesting topics to look into. Is Dreamer V2 also really fast? Like in terms of not in terms of sample efficiency, but in terms of wall time. Like how fast does it run?
I do know they use quite reduced resources when compared to Agent 57. I think 1 GPU, basically.
Okay.
And something around... Wait. I think I read somewhere 70 hours. I'm currently looking it up. You can look up hours instead.
Yeah. Oh yeah, due to the large computational requirement, a comprehensive evaluation study on this list of changes is unfortunately infeasible to us. This would require 55 tasks times 5 seats for 10 days per change to run, resulting in over 60,000 GPU hours per change. However, we aim to... Yeah.
This is the ablation study that they did not run.
Yeah. So it doesn't really help us. But in any way, so let's keep an eye out for new implementation, interesting algorithms, and maybe set something for the next monthly development cycle. And if you're also implementing PBG at the same time, if you have any questions or things you want to discuss, throw it into the monthly dev channel, and we can talk over there. Other than that, I don't have anything else.
What is this paper called again? I want to look it up.
Yeah. It's called Mastering Atari with Discrete World Models.
Do you think, I mean, without reading it at all, do you think it sounds like it's going to be discrete in the latent space, similar to like the VQ, VE stuff?
I haven't heard of that. VQA?
They do mention they have a discrete model indeed, unlike Dreamer.
Okay. I see. Yeah. All right. Yeah. Go ahead.
There was the author published it posted it on Twitter, and there was a comment related to the nature of the model itself. Was it discrete or continuous? I'm trying to pull it up right now, so I'll send it in the Slack if I found it.
Sounds good. Also, our 1 hour meeting time is sort of coming to an end, so I don't want to hold people here. So if you gotta leave, please feel free to leave. But if you want to stay and talk a little bit, I might have an extra 5 or 10 minutes or so. But yeah, do you guys have any questions or comments, any thoughts? Sorry?
Not really. I'd have to look into this a lot more.
All right. Sounds good. All right, I think maybe this is a good point to wrap up the meeting. Thanks everyone for coming. And we'll see you guys maybe next week as well.
Cool.
Likewise.
All right, you guys have a good weekend.
Yeah, you too.
Thanks, you too.
All right, I'll see you guys. Peace out.
Yeah.
See ya.